Good morning, students. In measurement of high voltage, we already see some methods of measuring high direction voltage, like with the help of sphere gap. Then we also saw the factors affecting the measurement in sphere gap. Then the Abraham voltmeter we also see, the uniform field gap, and the last one what we learned was electrostatic voltmeter for measuring our high direct voltage. Now we are studying the ammeter in series with high ohmic resistors. Here in the circuit we have given a resistor connected in series with the current measurement supply, and the overvoltage protection is connected across the current supply to protect our current supply method. Now for this is using for the measurement of high DC and AC voltage by means of ammeter in series with the resistor R. So using Ohm's law, we can reduce high voltage to measurable quantities. The simplest method to achieve this is by use of a microammeter in series with resistor R of sufficiently high value so as to keep loading of an HV source as small as possible. So here we can see the voltage across the resistor R will be R into I by using Ohm's law. So if the voltage drop across ammeter is neglected, then for DC voltage measurements, average current indicating instrument such as moving coil or equivalent electronic meters are used, which gives arithmetic mean value of V according to the Ohm's law, V equal to IR. So with the help of ammeter connected in series with the high value of R, we can also measure our high voltage volt. Now the another method is potential divider. So here across low resistance R2 or we can say Z2, electrostatic voltmeter or high impedance voltmeter is connected. So the low resistance R2 or Z2 and potential divider are connected as shown in this figure due to sudden changes in voltage caused by first switching operations or flashover of test voltages or short circuit flashover or damage may occur divider elements. This is due to stray capacitance across the elements. So here the low resistance R2 and potential divider are connected, and due to sudden changes in voltage caused by switching operations, flashover test voltage, short circuit flashover or damage that may occur and can damage our divider elements. This is due to stray capacitance across the elements. To avoid such transient voltages, voltage controlling capacitors are connected across the elements. So with potential divider for high voltage, we can say V1 equal to V2 into summation of R1 plus R2 divided by R2. This is the formula. Now for potential dividers, the accuracy is we can say as follows: up to 100 kV the accuracy will be 0.05%, up to 300 kV the accuracy will be 0.1%, and also up to 500 kV the accuracy will be 0.5%. So with using potential divider we can also measure our voltage. Now the another method is generating voltmeter and field sensor. We can also say GVM. So what is the principle of this type of measurement? We can say the generating voltmeter comprises essentially for an insulated stator mounted facing the high voltage terminal. It is periodically shielded from this high voltage terminal by the rotation of a grounded sectored disc at a constant speed. The stator to terminal capacitance is thus caused to vary periodically, which induce a stator current, which is the measure of a terminal voltage. It is rectified with a precision rectifier and is read on a digital meter. It is well known that the flow of current in a capacitor takes place due to the rate of change of charge. So the current I follow this equation ut into dc by dt. Here ut is a terminal voltage, C is a terminal signal plate capacitance. So we can also write I equal to minus dq by dt, where q is a charge in a capacitor, and also we know that the q equal to cv. Here C is the value of capacitor and V is the voltage applied to this capacitor. If C and V are both variable, then the expression of the current is given by this. I equal to minus dq by dt. Here we have differentiate q equal to cv and substitute this value cv into and differentiate it value. So cv, it is a multiplication, so in first c term will be constant and the differentiation of v will be occur, and then addition now v will be the constant term and the term c will be differentiate. So when a capacitor is connected to a DC source, the capacitor can only be charged, but the current flow is not possible unless there is a rate of change of charge. If there is a rate of change of capacitance, the current flow is possible in case of DC also. So we can also say that I equal to minus V into DC by dt, where dV by dt we put at a 0 due to not change of voltage. So this result current is a measure of the DC voltage under test. So the dome is placed atop a epoxy made insulated sheet rested over cylindrical insulator. The GVM is placed in a circular groove in a earthed metallic sheet above dome top. The metallic sheet is supported by epoxy nuts over 4 numbers of threaded insulating rods of epoxy mounted at the 4 corners of the sheet. The distance and the angle of the metallic sheet and hence the GVM with respect to the dome is varied by sliding the nut supports of the sheets mounted on the 4 threaded rods. Hereby we can take measurements as measurements can be made with GVM rotated at a constant speed of 1000 rpm. So measurement at linear distance of 135 mm, 150 mm and 200 mm between the GVM and the dome top can be taken with GVM kept parallel to dome base plate. The advantages of generating voltmeter are loading effect is eliminated, power circuit and measuring circuit is isolated, the scale is linear and range extension is convenient, can be used comfortably with Van de Graaff and partial acceleration, but there are also some disadvantages. Construction is delicate and complicated, auxiliary drive is needed and difficult to handle due to bulky size. Calibration is frequently required as change of position changes the calibration. So this is the advantage, disadvantage and the principal operation of GVM means generating voltmeter.